Hi guys, in this video I'm going to talk about what the gradient is and what the del operator is. And the learning objective is to understand what it means to determine the slope or rate of change in more than one direction, which is what we call the gradient. Okay, so I wanted to start with an example where we just have a field of values. So these are different measurements of something across two dimensions, the x and y dimension. Like the book gives the example of, this could be something like temperature or humidity, or it could even be height or something like that. And when you have a two-dimensional field of values like this, you can ask yourself, not just what is the rate of change in general like we would do for a one-dimensional function, but you could ask what is the rate of change in each individual direction. So in the x direction, well, if I take any of these two values of my field and divide it by the difference in the x direction, I'll just pick 2, right? I can do 2 minus 2 over 4 minus 3, right? I would get 0. There's obviously no change in the x direction. And actually, I'm going to move this down here. But what about the y direction? Okay, there is a rate of change in the y direction. Here, the values change by 1 when the y value changes by 1, but here they change by 8 when the y values change by 8. So there is a slope or gradient in the y direction, but there isn't one in the x direction. I want to come up with some kind of quantity that can describe, right, this behavior of this particular field of values, okay? And that quantity is the gradient. Okay, but let's think about what it actually is. So what the gradient actually is a vector. Okay, it is a vector sum of the rate of change in the x and y direction. So if this is the rate of change in the x direction, and this is the rate of change in the y direction, okay, when I add these two vectors together, I'm going to get the total rate of change. Okay, so this is the gradient vector. Okay, so let's think about what the gradient vector would look like for this particular field of quantities. Well, it's going to change depending on where I am in x and y space. I know for this particular field that the gradient or the component of this vector in the x direction is always going to be 0, but it's going to change in the y direction. Okay, so actually let me move this over a little bit further. So for this particular field of values, you know, here I might draw that gradient vector small, just has a y component, and we'll start it pretty short, but as I go up here, it's going to start getting bigger, and I don't want to draw too many of these because I think you guys know where I'm going with this. Okay, and then if I go, that all should be the same, a little bit higher, right? I'm going to draw these vectors even longer, okay? Not to scale, by the way, just kind of eyeballing it, but you get the idea. I can look at this field of vectors and it tells me something about the rate of change, okay, of this two-dimensional field of values. Okay, that's what the gradient does. All right, we can look at another set of values. Here's a set of values that have a non-zero rate of change in both the x and the y direction. You can challenge yourself and pause the video and see if you can come up with a function that describes how these values are changing in the x and y direction. Of course, your function will be continuous in the way I've drawn these values. They're discrete. Okay, the right function that describes these values, okay, is this one. So it's the x value times 2 to the y minus 1. So if I plug in the various x and y coordinates into this function here, I'm going to get the values that I wrote here in this grid. Okay, I can also use this function to come up with a continuous rate of change in the x and y direction. And I do that by taking something called the partial derivative of the function. Okay, so the partial derivative basically means I'm only going to take the derivative with respect to one variable at a time. So here I'm only taking the derivative with respect to the x variable, and so I can assume that the y variable is a constant. Essentially, I can ignore it, okay, treat it like an a or a b or whatever else, okay? So this one's easy to take if I just do the x direction. And I do want you guys to note, when you're taking a partial derivative, there is some special notation. A total derivative or a full derivative has an actual d. This is kind of like a script d, okay, or like almost like a delta, but not quite. Let me finish writing this. Partial derivative. Okay. If I want to take the derivative of this function in the y direction, that's actually a little bit trickier, and I have to admit I had to look this up in a table of derivatives. I couldn't remember how to do it. So you get x times 2 to the y minus 1, okay, and then you get natural log of 2. This might be really familiar because you guys just had some calculus. Okay, and then if I do the chain rule, I get a 1, but I'm just going to ignore that. Doesn't do anything for me. Okay, so now my gradient vector, it's still going to change as I slide it around, okay, in this space. The actual length and the direction of it will change. But if I want to figure out what the components of that vector are, let's say I want to evaluate the gradient at a particular point. Let's call it just x and y. In order to do that, I have to figure out the two components of my gradient vector. The y component is going to be given by the function, the derivative of the function in the y direction evaluated at that point. Okay, and I'm just making up some links here. Same idea for the x direction. When I add those two together, I will get the gradient vector at that point. Okay, so I'm going to show you at the end of this lecture how you can use Mathematica to actually make the calculation to find this kind of gradient vector across a field of values. But I do want to note right now, let me make this a little bit bigger, that I'm doing this example in 2D because I'm writing on a sheet of paper. Okay, but the gradient vector can also be evaluated across a three-dimensional field. So imagine, again, the temperature of the air in the room. That could be changing in 2 dimensions, right, x and y direction, but also in a z direction, which could be the vertical direction. Okay, so what we're really trying to do is represent the multi-dimensional slope of a function or field of values. Okay, and I'm doing that by analyzing the rate of change in the different directions. Okay, and what results is a vector. Okay, and mathematically speaking, I'm going to take the gradient of a function or a scalar field of values. This is a function or scalar field of values, which is to say I actually cannot take the gradient of a vector field of values. We're going to do some vector analysis later in the week, but right now this t, which is defined in your book, is a scalar. It's not a vector. Okay, so I'm going to take a gradient of a vector field of values, but I'm going to evaluate that slope in more than one direction, and I'm going to do that by, right, taking the partial derivative of that function, okay, in the different directions, and I'm going to use that to build a vector, okay, that has components that look like that. Okay, so this tells us the size of the slope, that would be the magnitude of the vector, and the direction of the slope. A good way to think about it is if you think about taking the gradient of a slope, if you're standing on a slope, the gradient vector is going to point in the direction, so wherever you are, in the direction where the slope is the steepest. That'll give you the direction the gradient vector is pointing. And then depending on how steep that slope actually is, that vector will be longer or shorter. Okay, so if you can imagine, if you were looking at these vectors that you would draw by walking around this surface from above on a flat map, you'd actually be able to see how the slope of that mountain changed, even though you were looking down on it on a two-dimensional map. Nope, and you know what? I should have drawn a vector sign on that. Let me draw it here. Okay, the del operator is a vector operator. It's not actually anything on its own. Okay, but if I look it up in a book or in a table, this is what they're going to give me in Cartesian coordinates. Okay, it would have a different form in cylindrical or spherical coordinates. And the reason for that, by the way, is if you think about, if I want to use spherical coordinates to describe the rate of change of something like topology, I need to do some kind of funky trig in order to figure that out. Because if I think about moving on the surface of the Earth, if I'm at really high latitudes and I go 1 degree in longitude, so say I walk around the Earth a little bit up near the pole, I'm actually traveling a lot shorter distance, right, than if I travel 1 degree of longitude near the equator. Okay, so I need to have some kind of sophisticated geometry in my gradient function in order to make sure that the gradient near the pole means the same thing as the gradient near the equator. So you can go in and actually derive these things and figure them out, but sometimes it's sufficient just to look it up in a table and then understand why it might be complicated, and it has to do with that. Okay, so a few more things about the del operator that the book also points out. This operator, it's kind of like just looking at one of these partial derivative symbols. It's meaningless on its own, okay? Doesn't really mean anything if you read it all by itself. It's an operation, kind of like, right, this notation that we use to take the partial derivative, okay, that must be applied to a function to have meaning. Which is to say you cannot draw the del, right? I couldn't draw a graph of the del operator all by itself. Okay, so let's take a little break, and I'm going to open up Mathematica and just show you how to calculate these fields of gradient vectors using Mathematica.